All right, how's it going, guys? More notes. Today we get to talk about a topic called drag force or velocity-dependent forces. This has come up in class, and I usually just say, oh, don't worry, we're not worrying about the drag force yet. But now I'm going to teach you about it. So if there is a drag force or any sort of air-resistant force, now you'll know how to handle it. A lot of times these will show up in AP tests. It will not always be called a drag force. Sometimes it'll just say a resistance force, but they will all be solved in a very, very similar manner. So once you know how to solve one of these types of problems, you should be able to just go through these steps to solve any of them. All right, so what we have with a drag force or a velocity-dependent force would essentially be air resistance. So there are a lot of ways this can come up. We could have, a car driving and encounters a resistive force, or we could have someone in the air falling towards the ground. That's the example I'm going to go through and talk about today. But again, these all get solved in the very similar manner. So here we're going to say I've got a object, it's falling, so the force of gravity is acting on it, and there's upwards force, which I'm going to call air resistance. F, air resistance. This is the opposing force. We're going to say that it is velocity dependent. So the faster the object is moving, the greater the velocity. We can say it's equal to B times V. B is what we call a proportionality constant. So the force is related to the speed. The proportionality constant we're calling B. This will not necessarily be equal to BV. It could be equal to BV squared or BV cubed, whatever they feel like telling you. But the point of the story is that the air resistance force is equal to B, the proportionality constant, times something related to the velocity. Awesome. If we look at this mathematically, BV is opposing mg. So we could write what we call a differential equation. Differential equation. Differential equation is a fancy way of saying Newton's second law. If you see this in any of your AP tests and it says, oh, write a differential equation, what you're going to want to say is, well, we know F equals ma. So F is going to equal m times dv dt. If you wanted, depending on how you're solving it, if you're solving it in terms of velocity or position, you could also, it's F equals m d squared x over dt squared. That is Newton's second law in differential equation form. So if you hear, oh, differential equation, you're going to write F equals ma in dv dt form, which means differential. To make it specific for this situation, we could look at our two forces we have here. The air resistant force is up, force of gravity is down. I'm accelerating downwards. So what I can write is BV minus mg is going to equal negative m dv dt. Essentially, up we made positive, BV is up, mg is down. We are accelerating downwards, so it's equal to negative ma or negative m dv dt. This right here is the equation that explains the motion of this object. So this is the equation that, spelling wrong, that governs this motion. There we go. So BV minus mg equals negative m dv dt is our differential equation. It's differential equation because we have the dv dt, there are differentials. Our air resistance force is up. It's BV, which is our proportionality constant, times speed. Again, it might be BV squared or whatever, minus the force of gravity, and that is our differential equation. Conceptually thinking about this, let's think, okay, at time t equals 0, we drop this object. This speed is 0. Technically, this is in free fall at this moment. As then the time increases, our velocity is going to be increasing. As our velocity increases, our air resistance is therefore also going to increase, which means our acceleration is actually going to be decreasing as our velocity is increasing until we get to a point where BV minus mg is equal to 0. That is the point at which it no longer will accelerate. That's the limit of this. BV cannot be greater than mg. If BV is greater than mg, then that's telling us that air resistance is actually pushing it up, which doesn't make sense. Objects, when they're falling, they're going down. They're not accelerating upwards when you drop something. So BV is approaching a limit up until where the acceleration is 0. We can call that our terminal velocity. It can't go any faster, and BV is therefore equal to mg. So if I want to solve for Vmax, that occurs, again, when the acceleration is 0, BV equals mg, so mg over b. It's worth noting the units of velocity are meters per second. So the units of mg over b must be meters per second. Units must be meters per second. So a lot of times an AP problem will ask you for what are the units of b. So you can say, well, mg over b has to equal meters per second, so you can do some math to figure out what the units for b would be. You could try that. It ends up being, in this case, kilograms per second. Again, it's going to vary depending on what function they give you for your air resistance force, but the velocity max will have to equal meters per second. Solving these is done by a method called separation of variables. I'm going to save that for the next video. This is really just to talk about conceptually what's going on. So just one more summary conceptually. If you have an object in free fall and we are including the drag force or the air resistance force, that means that we have a velocity dependent force. So the air resistance would be up in this case. It's the proportionality constant times the velocity. Again, it could be v squared, it could be anything else. This is just where you're going with BV for this example. So if I want to write the differential equation that governs this motion, I should start with F equals ma in differential form. So F equals m dv dt. My net force, I have BV going up, mg going down. The acceleration is down, so negative m dv dt. That boxed equation right there is our differential equation. Solving it, we would want to use separation of variables, which I'll do next video. Looking at it, the max speed we will ever hit will be when our upwards force equals our downwards force. So mg over b is our max speed. Initially, when you drop it, your speed is 0. At that moment, we are in free fall. And then our units of mg over b, since that is a max speed, should be meters per second. Conceptually, I hope that made sense. Hopefully I got everything important in here. We will delve into the mathematics of solving the differential equation in our next video. All right, awesome. Talk to you guys later. Bye.